Section 4.7 is one of my favorite sections out of the trigonometric portion. Uh, for every function, we need a way to undo what that function does. And the inverse trigonometric functions give us a way to undo all of our 6 basic trig functions. So now what we're going to be talking about in this section is we're going to be understanding and learning how to use the inverse sine, inverse cosine, and inverse tangent functions. And then we will use our calculator to evaluate inverse trigonometric functions, and then find exact values of compositions of inverse trig functions within trig functions and vice versa, trig functions within inverse trig functions. So first of all, when we think about an inverse function, I need you to remember that only one-to-one functions have an inverse. So, like, for example, we discussed in the algebra portion, we said, well, y equals x squared does not have an inverse because it's not a one-to-one function. So what we had to do is we said, well, while the whole function doesn't have an inverse function, we could restrict it to values from 0 to the right and just be the right wing of y equals x squared and say, well, that portion is one-to-one, thus it has the inverse. And we say the inverse of y equals x squared for x greater than or equal to 0 is just y equals the square root of x. So now in this same manner, the sine function overall certainly is not one-to-one. It's going to have infinitely many y values for many different x value. So you can say, or I should say, infinitely many different x values for one y value. But we can say, well, what if though we restricted it from negative pi over 2 to pi over 2? Now, a common question is, well, why restrict it from negative pi over 2 to pi over 2? Why not go from 0 to pi or 0 to 2 pi? That'd be a terrible idea. And you see here why. Because I can't restrict it from 0 to pi because it's not one-to-one in that region. Well, why not just restrict it from 0 to pi over 2? It's one-to-one in that region, and it is. However, it doesn't take on all the values the sine function can take on. So whenever we're thinking of what domain to restrict these trig functions on, we think, well, it needs to be a domain close to x equals 0 that involves all values that the y all values of y that the function could ever take on. And we can say, well, that is easily seen from negative pi over 2 to pi over 2. It takes on all y values from negative 1 to 1. However, it's one-to-one in that region. And so we can say, if we restrict it to that, then it can have an inverse for the inverse sine of x. So now, it looks like sine raised to the negative 1 power. Please remember, whenever you see that, though, that is literally means the inverse of the sine function. So we read it as y is equal to the inverse sine of x, or at x. Now, and it's just the opposite of what the sine function does. So if we say y is equal to the inverse sine of x, that means that the sine of y is equal to x. You should be able to take the sine of both sides of your equation. And when you do that, the sine and the inverse sine would cancel each other out, and you get, well, y is equal to the sine of x if and only if the sine of y is equal to x. Now, whenever we graph out the portion of the sine function that can have its inverse from negative pi over 2 to pi over 2, it looks like this. Now, from whenever we graphed inverses before, you're supposed to remember the graph of an inverse is just going to be a reflection about the line y equals x. It's going to switch each of the ordered pairs. So xy values in the original graph become yx values in the inverse. So the ordered pair pi over 2, 1 becomes 1 pi over 2 in its inverse. Remember, pi over 2 is approximately 1.57. And the ordered pair negative pi over 2, negative 1 becomes the ordered pair negative 1, negative pi over 2. So the inverse sine function, actually, it looks similar to the sine function in this region. It just has a domain of negative 1 to 1 and a range from negative pi over 2 to pi over 2. But unlike my sine function that would keep on going forever and ever and ever, this is it. That is the only portion of the inverse sine function that is ever defined. It has that very restricted domain. So its domain has to have the restricted values from -1 to 1, because you can say, well, the x values of the inverse were the y values of the original function. You can say, well, you know that the y values of the original function were from -1 to 1. So you could never put in a value inside of an inverse sine function outside of -1 to 1. So if I said, hey, what's the inverse sine of 5? You'd say undefined. What's the inverse sine of -2? Undefined. Why? Well, because inside the inverse sine function, the domain can only be a value between x equals -1 and x equals 1. And it is literally asking you, at what point does the sine function have that value? So if I said, for example, what is the inverse sine of 1/2? It's literally asking you what x value on the sine function gives you a y value of 1/2. And you say, oh, I know that at pi over 6, gorgeous. The sine of pi over 6 is 1/2. That's the very first angle on our unit circle. I can go over here and say, well, yeah, at pi over 6, the y value would be 1/2. Well, then I know on the inverse sine function, the inverse sine of 1/2 would be pi over 6 for the y value. So now let's talk about that some more as far as finding inverse trigonometric functions. So just like I was saying before, you're going to have to know forwards and backwards what your sine function is on the domain that the inverse sine is defined. That's from -pi/2 to pi/2. Now we should know our sine function for all values on the unit circle, but specifically for the inverse sine, you've got to concentrate on quadrant 4 and quadrant 1. And the quadrant 4, instead of calling it angles between 3 pi/2 and 2 pi, we have to do the negative rotation and say, well, it's -pi/2, -pi/3, -pi/4, -pi/6. At -pi/6, our sine function is -1/2. At -pi/4, it's the negative square root of 2/2. Positive pi/4, it's the positive square root of 2/2. And we know that this relationship occurs because the sine is an odd function. If you change the sign of the angle, it changes the y value sign. So I know all of these values on the sine function. Because I know all of those values, there's no way I won't know the inverse sine for anything. So now when I give you a problem such as find the exact value of the inverse sine of the square root of 3/2, there's no question what it is. You're saying, okay, then this is literally asking me at what point is the sine function the square root of 3/2? And you should be thinking, well, that's at 2/3 of the way up through quadrant 1. That's going to be at an angle of pi/3. Now, if I go back to my previous page and say, yeah, at pi/3, the sine function is the square root of 3/2. So now we're inverting that. This is your independent and dependent variable on the sine function. So on its inverse, this is the independent. The dependent answer is your pi/3. And so I'm literally going in and saying this is the same thing as asking you when is the sine of theta the square root of 3/2 on the interval -pi/2 to pi/2. And just quickly looking at this, you know that occurs at your pi/3 here. So now I can say, well, that's not bad at all. Now, something that students get confused with is they'll say, well, why can't it be two answers? Because they'll say, well, if it's when the sine of theta is the square root of 3/2, why can't I say pi/3 or 2 pi/3? And please keep in mind, it can't do that. Why can't it do that? Because it's an inverse sine function. For every x, there must be one f of x. So for every input, there must be one output. That's why we had to restrict the sine function to be between -pi/2 and pi/2. So we would guarantee that no matter what value we input into the inverse sine function, we're going to get one value out. And the value that we get for when the sine function is square root of 3/2 is pi/3. Now, if I were just solving this equation, yeah, it's pi/3 and at 2 pi/3. But for the inverse sine, it's specifically restricted to this domain. So I can say, my only answer is pi over 3. You will only ever get one answer to an inverse trigonometric function. Now, what if I ask you what's the inverse sine of the negative square root of 2 over 2? You should automatically be thinking, well, this is just when the inverse sine, or sorry, when the sine function is the square root of 2 over 2, that's going to occur in quadrant 4 at the midpoint. If I were thinking of the positive unit circle, it would be at 7 pi over 4. But in order for the inverse sine to exist, I'd say, nope, I have to call those negative values because the inverse sine is defined such that the sine function starts at negative pi over 2 and ends at pi over 2. So that midpoint of quadrant 4 can also be called negative pi over 4. I know my answer here for what is the inverse sine of the negative square root of 2 over 2. It's negative pi over 4, guaranteed. Now, the way I know that is because I'm just thinking of the angles between negative pi over 2 and pi over 2. These are all the sine's values. The inverse sine of negative square root of 2 over 2 is literally asking you, when is your sine function that value? The answer to that question, negative pi over 4. Now, please do keep in mind, I know, and you should also know, that if I were just asking when the sine of theta is the negative square root of 2 over 2, you could say, well, it's also that value at 5 pi over 4. That's not part of the domain that we're worried about, though. So the only answer is our negative pi over 4 for the inverse sine. Now, if we talk about the inverse cosine, similarly to the inverse sine, you'd say, well, I'm going to have to restrict this function because this function is certainly not a one-to-one function. So unlike the sine function, trying to restrict it from negative pi over 2 to pi over 2 would be a horrible idea. It's not one-to-one in that interval. However, if you look at the region of this curve I have highlighted, I can say, but the cosine function is one-to-one if I restrict it on the interval starting at 0 and ending at pi. It takes on all y values the cosine function can ever take on, and it's certainly one-to-one in that region. So now I can say, okay, I'll restrict my cosine in between that interval, and when I know that the y values always goes between -1 and 1, that the x values, please notice, will go between 0 and pi. So when I'm talking about the inverse is going to flip those two, and I can say, well, then the y values of the inverse are only going to ever be positive. They're going to be between 0 and pi. That's what I'm saying here. On the inverse cosine function, its range is going to be 0 to pi, and its domain is going to be -1 to 1. So this is kind of strange. The inverse cosine function could never be a negative value. You can see that now on this graph. I've graphed out the portion of the cosine function that does have an inverse. We have to restrict it from the interval 0 to pi, and it takes on y values starting at 1, going down to -1. So now, whenever I flip those ordered pairs, I'd say, well, this ordered pair here, pi -1, its inverse is going to give me the point -1 comma pi. I start off up there, and then I would go down and I would include the point 0 pi over 2, and I would include the point 1, 0, and then I would connect those dots and I'd say, yeah, there's my inverse cosine function. It starts abruptly at -1, ends abruptly at +1, can never ever have a domain outside of that. So again, if I ask you something like, well, what's the inverse cosine of 2? Does not exist. That is literally asking you, hey, when can the cosine function be 2? And you know it can't be. Cosine has a range of -1 to 1, so the only values you can plug into the domain of the inverse cosine function are values between -1 and 1. And the only values we'll ever get out are between 0 and pi. Now, when we talk about evaluating an inverse cosine function, you need to have a very good understanding of the values of your cosine function from 0 to pi, because that's where the inverse cosine is defined. So like, for example, if I said, hey, what's the inverse cosine of 0? You should quickly say, well, the inverse cosine of 0 is pi over 2. Why? Well, because the cosine of pi over 2 is 0. What's the inverse cosine of 1/2? Pi over 3, because the cosine of pi over 3 is 1/2. Now, on this page, I'm asking, well, what's the inverse cosine of negative 1/2? I can say, well, okay, that's going to put me in quadrant 2. At negative 1/2, my angle should be 2 pi over 3. Now I can say, well, I need to find that though. So, well, I've already found it as far as what I think in my head. As far as showing you, I would literally be thinking it's trying to solve when the cosine of theta is negative 1/2. Now, just thinking of my knowledge of the unit circle, that occurs at 2 pi over 3 and again at 4 pi over 3. But the only angle such that the inverse cosine is defined, since the cosine has to be restricted between 0 and pi, is 2 pi over 3. 4 pi over 3 is outside of the bounds of the inverse cosine function. So I can say, okay, should be 2 pi over 3. It is, because the cosine of 2 pi over 3 is negative 1/2. Then the inverse cosine of negative 1/2 is 2 pi over 3. Glorious. Now, the inverse tangent function. You should remember the tangent function looks like this. It has vertical asymptotes at negative pi over 2 and pi over 2. That makes it very easy to see. Oh, after that, it merely just repeats itself. And after that, it would not be a one-to-one function. So we're going to need to restrict the inverse tangent function similar to the restriction for the inverse sine. Now, it's not the same. The restriction for the inverse sine went from negative pi over 2 to pi over 2 and included the endpoints. You had brackets. Here, we go from negative pi over 2 to pi over 2, but since those values are not defined for the inverse tangent function, then in the range of the, since they're not defined for the tangent function, then the range of the inverse tangent function cannot include those values either. So we will restrict the domain of the tangent function to be between these asymptotes. And then I can say, well, then if that's the case, then I know that the range of the inverse function is going to start at negative pi over 2 and go to positive pi over 2. Now, unlike the inverse cosine and inverse sine, which have a very restricted domain, notice the range of the inverse tangent function takes on all values. And you think, well, why? Well, look, instead of a sine and cosine function that's oscillating between negative 1 and 1, your inverse tangent function has a range from negative infinity to infinity. So the domain of the inverse tangent function is any number between negative infinity and infinity. If we graphed these functions out, here's your original tangent of x with our 3 common points there. Then if I say, well, I want to take the inverse of that, I know that the inverse of these vertical asymptotes are going to be horizontal asymptotes. Instead of vertical asymptotes at x equals negative pi over 2 and x equals positive pi over 2, you say, well, then you're just going to have horizontal asymptotes at y equals negative pi over 2 and y equals positive pi over 2. And then instead of it looking sort of like an x cubed function stretched between those two vertical asymptotes, it looks more like a cube root of x function that's going to approach those horizontal asymptotes as x gets large or as x gets small. Now I can say, well, all right, I took the inverse of all of these points within. Pi over 4, 1 becomes the point 1 comma pi over 4. And then negative pi over 4, negative 1 becomes the point negative 1, negative pi over 4. So when you're asking, hey, what's the inverse tangent of negative 1? It's literally asking you, at what point is the tangent function negative 1? And you'd say, well, it's at negative pi over 4. That's why the y value here is the answer, negative pi over 4. Now, if we think about that within some problems, again, if you know the y values of the tangent function, it makes it very, very easy to take the inverse tangent for common values, such as if I just said, well, what's the inverse tangent of 1? You'd say, well, the inverse tangent of 1 is pi over 4, because I know that the tangent of pi over 4 is 1. Now, again, you might be thinking, but the tangent is also 1 at 5 pi over 4. That's true, but it's not part of the domain of the tangent function that we have to restrict it to in order for the inverse tangent to exist. So we only need to worry about common values between negative pi over 2 and pi over 2. So notice I didn't even plug in negative pi over 2 and pi over 2 into this chart because they would be undefined values. Now, when I do the inverse tangent, I can say, well, let's take the inverse tangent of -1. And you should automatically say, well, that's at the midpoint of the quadrant 4. And if you're going around a unit circle, it'd be 7 pi over 4, but we have to go negative angle. So you said, well, that's the same thing as negative pi over 4. I know that the inverse tangent of -1 is negative pi over 4. Now on the next page, I'm showing where I'm getting that because the tangent of negative pi over 4 is -1. I can say the inverse tangent of -1 is my negative pi over 4 here. So it makes it pretty straightforward to do most of these problems. Now, what if I were to have said the inverse tangent of the negative root of 3? You can see, well, since the tangent of negative pi over 3 is the negative root of 3, you can say the inverse tangent of the negative root of 3 would be negative pi over 3, and so forth. Our three graphs of the inverse trig functions, do you have to have their graphs memorized? No, but it's probably a good thing to, just keeping in mind. Now, probably more so than anything, the domain and range of each of these. So the domain, you can only plug in values between -1 and 1 in both your inverse sine and inverse cosine. The only answers you'll ever get for any inverse sine function is a value between negative pi over 2 and pi over 2. The only answers you'll get out of an inverse cosine function is an angle between 0 and pi. And then the only answers you'll get out of an inverse tangent function is an angle between negative pi over 2 and pi over 2. And keeping in mind, you can plug any angle you want into that function. Now, if we talk about calculators, this is a page where I just want you to kind of test your ability to use your calculator. I put some values here. And please keep in mind, whenever we're doing these, if I say something like use the calculator and find the value to 4 decimal places for each function, our answers are going to be angles. Now, it just depends whether you want your answer in radian or degree measure. Unless it specifically says degree measure, then radian measure is wanted. So when this is saying the inverse cosine of 1/3, that is literally asking you at what point on the unit circle is the x component going to be -1/3. And you can say, well, I know that has to put me over into, sorry, not -1/3, 1/3. The inverse cosine of +1/3. I'm looking at it correct now. I know that has to be the x component where the x value is 0.3 repeating. That's going to be a little bit greater than a pi over 3 angle, because at pi over 3, I know my cosine is 1/2. But it's not quite to pi over 2 because at that point my cosine is 0. So I can say, well, yeah, in this case, I can use my calculator and it gives me the angle between pi over 3 and pi over 2, in this case, 1.231 radians. Whenever you have a radian answer, there is no need to write out radians. It's implied to be in radians unless you put the degree. And of course, you don't want to put the degree here because this is a radian answer. Now, if I want the radian angle measurement for the inverse tangent of -35.85, then I can just say, well, all right, this is asking you at what radian angle measure is the sine going down 35.85 times more than the cosine is moving to the right. And as you would suspect, that's almost straight down. Straight down would be negative pi over 2. This is -1.5429 radians. And again, when your answer is in radians, you don't have to write it out. Now, page or example 5. I'm asking you to evaluate, if possible, the cosine of the inverse cosine of 0.7. Now, almost all the time, especially in the basic examples, a function and its inverse will cancel each other out. The only thing you have to be aware of is whether there's any domain restrictions or if they exist at a certain value. So when I'm looking at inverse cosine of 0.7, I say, yeah, that exists. The domain of the inverse cosine function is just, you have to put values between -1 and 1 in there. So whatever the inverse cosine does to 0.7, the cosine will undo. These inverse functions cancel out each other, and I'm just going to get 0.7. Now, that confuses students because they're like, well, I wish it were always that way. It's not always that way. Here's the reason. So if it were always that way, you would think the answer to the next problem is pi. Well, think about that. It can't be. Why can't it be? Because what you're supposed to remember, okay, inverse sine has a range. It can only give you a value between -pi/2 and pi/2. So you say, well, all right, in this case, it should give me an answer of pi. It can't. It's not physically capable of doing that. It can only give you an answer between -pi/2 and pi/2. So then a student might think, well, then it's undefined then, isn't it? No, it's perfectly defined. But in this case, they simply don't undo one another. You have to work one and then you work the other. So you say, well, okay, I can find the sine of pi. That's super easy. The sine of pi is 0. And so then, and that's what I should have put right here. Sorry, guys. That's what I should have put right here. This should be a 0. The inverse sine of 0 now is asking me, at what angle is the sine function 0? And you say, well, that's at an angle of 0. So the inverse sine of the sine of pi will give you the angle at which the sine function has the same value as the sine of pi. And you say, well, the sine of pi and the sine of 0 is the same thing. They're both 0, but it's only capable of giving you the answer 0. It's not capable of giving you the answer pi. So you say, well, the inverse sine of the sine of pi is the inverse sine of 0, which is 0. Now, what about the cosine of the inverse cosine of -1.2? Hopefully, from what I said earlier, you already know that's not even possible. Why? Because you can't plug any number other than a value between -1 and 1 inside of an inverse cosine function. So I would say, since -1.2 is not included in the domain of the inverse cosine, this function's not defined. You can't get rid of that function if the inside function doesn't exist in the first place. So this is not a case where you just say, hey, isn't it equal to -1.2? No, because the cosine of an undefined value is still undefined. And that does it for this section. Please, please work through the homework in 4.7. I absolutely loved doing it myself. I think once you're used to working these problems, they'll become fairly comfortable, or you will become fairly comfortable doing them, but they can present quite amount of confusion to begin with. So please let me know if there's anything I can help you out with in remedying some of that confusion. I'll be glad to help however I can.